Hello and welcome to Chemspec Digital 2021. I have the pleasure to introduce the first presentation in the Pharma Lecture Theatre. However, before I do, please note that we're recording the presentation to make it available to view on demand. Attendees are invited to write questions in the chat function from where we will read them out at the end. And now I will hand over to Dr. Hans Donkervoort of BASF Nederland, who will be presenting highly efficient PM use Nanoselect PT catalyst for aromatic nitro group reduction.
Yes, Jason, thank you very much for the kind introduction, and I'm really happy to be able to join Chemspec after such a long time, although it's still virtual, but having a chance to speak with other people and talk about new innovations in the field of catalysis for fine chemical materials. So as already stated, my name is Hans. I'm working with BASF in the Netherlands and in the catalysis area. And I wanted to share with you in the next half hour some of our latest developments with a focus on platinum catalysts that are used for specifically aromatic nitro group reductions. On the next slide, I briefly introduce to you what the area is that will be in the main focus. The area is comprising the precious metal powder catalyst, where BASF has a wide portfolio of materials available. We cover the whole range of precious metals going all the way from palladium through platinum, rhodium, ruthenium, iridium, and there are many variations available on different carriers, etc. There is a long history in the development and production of these materials within BASF, where we have over time generated production facilities all over the globe to be able to really follow the development of new materials, whether the R&D is being done in China and moving to India or to Europe or to the United States, or if the development is in the United States going to Europe, anywhere, we are able to follow that by supplying material to all those regions from a regional production facility. In all these years, we have really shown to be able to work together with customers and deliver a fast volume to market track record, allowing the fine chemical industry, as long as the catalyst is concerned, as far as the catalyst is concerned, to really move quickly and scale up on a need-to basis and with a good, efficient reproducibility. What you see is that in the recent period, there is a lot of focus of making catalysts more active and selective, because obviously, as you know, there is a the price of precious metals is fluctuating a lot, and therefore we have also generated, we comprise together the divisions that make available not only the fresh catalyst, but also offering the refining services and making very efficient use of the catalyst. So in the end, what we try to do is really enable highly efficient precious metal usage. And with that, hopefully short enough introduction, I really want to move into the area what is really the focus here, because enabling highly efficient precious metal usage, as you can see on this slide, is that what we have seen since 2016, especially in the palladium and rhodium market, there is a tremendous increase in prices of metal that is driving cost up of use of the metal. And obviously we looked into many different ways of mitigating that cost risk and making catalysts even more efficient than they are already. If you look, for example, to palladium, that's one quite developing in the upper trend. In 2016, the prices were down here, while at the moment the price is at $77,000 per kilogram of palladium. And if you compare that, or if you relate that to a standard 5% palladium on carbon catalyst, for example, and you take 1 kilogram of that catalyst, it actually contains palladium at a value of close to $4,000. For rhodium, it's even higher. Currently, a 1 kilogram of rhodium catalyst, 5% rhodium on carbon catalyst, contains a value of $30,000 worth of rhodium only. So obviously, if you look into that, you want to be able to lower your cost of use of precious metals. And on the next slide, I give you one of the examples, a recent example that we developed to do that, where you see that in a deprotection reaction, it's a debenzylation reaction, where typically 10% or 5% palladium on carbon catalysts are used. You can see that on the left side, the lighter blue bars. You see the relative activity level. What we did was we developed catalyst by modifying the carbon support, modifying the deposition technology. That gave a tremendous improvement in the actual activity in deprotection reactions. So a 10% palladium on carbon classic catalyst has approximately half the activity of these new blocking group removal catalysts. And that can either bring you higher productivity, you stay with the currently used classic 10 or currently used 5% palladium on carbon, but you double the activity. So you can improve your amount of product per hour produced, or it also allows you to go to a lower metal containing catalyst. A 3% palladium on carbon by weight of catalyst has the same productivity activity as a 5% palladium on carbon catalyst. That means that you effectively reduce your metal loading in the reactor by 40%. So this is one of the examples where you can really see that there are ways to improve the efficiency of precious metal catalyst. Another example, moving away from the activity, is going to, if you do use a catalyst, you all have experienced the fact that some metal can go into solution while doing the actual, for example, hydrogenation process. And obviously metal going into a solution will not be captured by the filtration system and can lead to higher metal losses. And what we have last year developed are catalysts which have a high leaching resistance. So I provide you here an example of a rhodium catalyst where the impact is quite significant. A customer, this is a real life customer, obviously I cannot share the name, but they're using a 5% rhodium on carbon catalyst where the overall metal recovery was leading to 78%. By moving to these leaching resistant catalysts, the metal recovery was improving from 78% to 90%, which if you quantify that, it is leading to a €2 million cost savings per metric ton of catalyst used, simply by the fact of not losing that much of metal. The same is also, we can also do that for platinum catalyst, where due to the lower metal price, the impact is somewhat lower, but still for each metric ton of catalyst used, a cost saving of close to €200,000 per metric ton of catalyst used. And in that specific case, another benefit, because you lose less metal, there is at the beginning, less metal needs to be mined. And if we get less metal out of the mines, it is also leading to a lower carbon dioxide emission number. And for the same example stated over here, more than 400 metric ton lower carbon dioxide emission is resulting from these leaching resistant catalysts used in the process. The third example is an example where it's related also to the blocking group removal catalyst, the deprotection catalyst that I already shared with you. It is how can we optimize the actual metal loading on the catalyst. We always start with 5%, or it's a very standard starting point in the industry. But we have several examples where the customer could change from a 5% to a 3% on equal catalyst dosage, so effectively lowering the metal loading by 40%. Another example is a customer where they were able to lower from 5 to 4%. They needed a little bit more catalyst, but still the cost savings are significant when you look to the amount of metal that goes into that process. And it's not only on the fresh catalyst side, but also if you use less metal in your process, also the recycling cost will be lower. And what we also see is that in many cases, you will see less metal ending up in your product. So it's really a quite an interesting way of lowering the cost of use of precious metals. Now, with that being stated, I now move to the Nanoselect technology, because all these examples that I've shown you here are based on the classic way of making a catalyst. And they are, as you can see here, quite good catalyst. But even a good, successful catalyst is not by definition perfect. This is an example of a 5% platinum carbon catalyst, and you can do very good performance testing. You can analyze that the dispersion, the size of the metal crystallites through CO chemisorption measurements is very good. But if you then look closer by using, for example, electron microscopy techniques, you see that this is a picture of a commercially available 5% platinum carbon catalyst. The black dots that you see everywhere are metal crystallites. And you see very small ones, somewhat larger, and also a big, well, agglomerate of smaller metal crystallites. And that obviously is not the most efficient way of making use of that metal. So if you then look on how the traditional catalysts are being prepared, you take a carrier, carbon, alumina, whatever, but let's say a carbon powder, that's the most commonly used carrier, and then you contact that carrier with metal. On the carbon, you have many different organic functional groups that act as the anchoring point for those metal particles. And when the metal is anchored on that carrier, you then reduce the metal on the support. Well, you can see already that carbon has many different functional groups on the surface, leading to, in principle, a different metal support interaction depending on the type of functional group where the metal is anchored. You cannot really control exactly where the metal is ending up. So there are many ways that a heterogeneous catalyst is even more heterogeneous than only by the fact that you can filter it off from your aliquot. And that is where we started to challenge our R&D colleagues to see what can we do to significantly improve the control of how we make those catalysts. And the way that was done was that we eliminate the support effect in the metal particle formation. There are examples in literature available that you can do that by reducing the metal in solution, forming unimodal colloidal particles. And you can control those particles while you make them. You can control by changing temperature, pH, solvents, etc. You can really you can predefine, I want to make 1 nanometer, 5 nanometer, 10 nanometer particles. And then once we have produced them, we then deposit them on the carrier, creating a heterogeneous catalyst. But now a heterogeneous catalyst where the size of that metal particle is completely controlled. And we check that in various situations, and you really see highly unimodal metal crystallites on those carriers. The way that was done on a commercially available production methodology, because that was really the big challenge. As I stated, this was reported already many years back in academia, but the technologies were simply not scalable or usable on industrial scale. And the solution that was developed by the R&D colleagues was that we use actually a stabilizer, which comprises not only a stabilizing functionality, but in the same molecule also the reducing functionality. And then the molecule that is depicted over here is also water soluble. So that allows easily scalable production of such catalyst. And we use that already for several different catalyst preparations, both in platinum and palladium area. And we now have this technology available on industrial scale. We can produce heterogeneous catalyst through this Nanoselect technology, presetting the metal crystallite size, and various palladium and platinum catalysts are available on commercial scale. So what we can now do is we can take certain reactions and see what would be the most optimal metal crystallite to make a certain hydrogenation reaction be done. And we did that also for aromatic nitric group reductions. For aromatic nitric group reductions, it's a multi-step process. It's not just one-step hydrogenation reaction as depicted over here. And there are some issues, especially in the final step. The final step can be slow, and what you need to do in that situation is you need to add a promoter to the catalyst. So having a platinum catalyst can be okay if the hydroxylamine that is formed as this intermediate, if you can convert the hydroxylamine immediately to the amine by a straightforward platinum catalyst, then perfect. But there are cases where this is actually building up as an intermediate, and then a promoter is required. So we looked into both of those systems to make a very efficient, high productivity catalyst for aromatic nitric group reductions. So if you look to it from a background point of view, as a chemist, what you see is that for several cases, the hydroxylamine buildup is leading to stalling of the reaction. That is something that we need to keep in mind. The other aspect associated with that is that hydroxylamines are unstable, and if they build up to a too high concentration, they can actually lead to explosions. So you really want to prevent the hydroxylamines from being built up. Then on the other hand, you have on the aromatic aromatic nitric group reductions, there are also selectivity challenges when other functional groups are present, and relatively high metal loadings are required. Currently, catalysts that are being mainly used in this area are sulfided platinum catalysts, which we do have available because they do work, obviously, but also we have a copper promoted platinum catalyst available, and in the market there is a vanadium promoted platinum catalyst being made available, which is considered to be one of the most effective catalysts for this reaction. On the graph on the right side, I actually show you what was found already several years back, that the activity of the catalyst in this specific reaction is actually depending on the metal dispersion. So this is an example where a structure-sensitive reaction is taking place on the surface of the metal. So this was an indication that the size of the metal crystallite, if we can control that, could lead to a further improvement in the performance of those catalysts. So we did develop, with that in mind, we screened various sizes of platinum crystallites, and we have now available on industrial scale catalysts that contain 0.8% platinum. We can make them on different carbon supports, and they show a very high, efficient, and good selectivity in aromatic nitric group reductions. I show you a couple of pictures. We zoom in on the carbon particle over here. You can see that now the bright spots are the actual metal particles. And you see that you can really close in, and all of those metal particles are really unimodal. So we can now make very efficient platinum catalyst for aromatic nitric group reductions. And we worked with a customer who had a challenge in this area to develop a very good catalyst for their process. They were using the vanadium promoted platinum catalyst, which was considered to be the best, the standard in industry. And you can see here the dark blue line being the hydrogen uptake curve in this specific process. What we then did was we first found an unpromoted platinum catalyst that showed intrinsically, the green line, very good higher activity. But as you can see, after approximately 60–70% conversion, the reaction more or less stalled, and it had to be prolonged, the reaction time for several hours to go to full conversion. As we indicated, this is coming from the fact that the hydroxylamine was built up and becoming quite a stable intermediate. So what we did was we actually promoted the Nanoselect platinum catalyst with molybdenum, and that is the pink line. And you see that now the reaction is continuing at the same good speed, and it is now over in the process faster than even the vanadium promoted platinum catalyst. I'll show you later some more specific details on how much faster and how good the selectivity actually was. Because what we then started doing was we started doing a scope investigation using these catalysts, comparing the molybdenum promoted platinum catalyst based on the Nanoselect technology with the vanadium promoted platinum catalyst on carbon. The objective of the scope investigation was that the yield of the aniline formed had to be more than 98%, and we looked at various R groups on ortho and para positions. Conditions were always kept the same at 30 degrees centigrade, 4 bars of pressure, and ethanol as the solvent. And this is an overview of some results that we obtained here. And you can immediately see what the benefit is. Using the vanadium promoted platinum catalyst for orthochloro-nitro benzene reaction, you see that the Nanoselect catalyst can be half the quantity of catalyst of metal can be used, and still you have even a faster conversion. So at half the metal loading, 0.11 milligrams of platinum versus 0.22 milligrams of platinum, you get a 98% selectivity to the aniline, while the reaction time to full conversion is still under 20 minutes versus 200 minutes with the vanadium promoted platinum catalyst. And this you see for all the other reactions as well. I notice now that there is a typo here. It says over 90%, but this should be over 99% selectivity for the dichloro compound. Again, still faster than the vanadium promoted platinum catalyst. And also you can do these type of very selective nitro productions in the presence of a nitrile, where the nitrile is not being hydrogenated. And really, in all those reactions, you can see that the amount of metal required is lower or similar, but then when it is similar, the reaction time is significantly higher. So you can also lower the amount of catalyst if required while maintaining the same productivity level. Please note that in all those reactions, when we took samples from intermediate stages, we did not see any hydroxylamine buildup. So that also from a safety aspect is a quite good thing. And if you then look in total to what we now have available, is that the Nanoselect catalyst is really delivering unimodal metal crystallites, which allow significantly lower metal usage in reactions. And for aromatic nitro group reductions, the cost saving per metric ton of catalyst used, for example, can be significant, over 100,000 euros per metric ton of catalyst in the loop of use of catalyst. There's one statement here, I should have taken it out, but it's an example of a palladium catalyst where we actually replaced the Lindler catalyst with a palladium catalyst where the lead can be taken out. But okay, if you have any interest in that, you can certainly get in contact with me, and we can tell a little bit more about that. So as a conclusion, we do have commercially available Nanoselect production technology developed that bring now platinum catalyst on the market for aromatic nitro group reductions, but also for other reactions. They can be screened. But in this presentation, I hope I show you that the platinum catalyst, where the size was optimized for aromatic nitro group reductions, are very efficient, allowing a 50% lower platinum content in your reaction while keeping the same activity and selectivity in the process. The same has been, as I already indicated, done for palladium catalyst, where specifically an example is listed over here, the replacement of the Lindler catalyst by a lead-free pure palladium catalyst, optimizing the metal crystallite of the palladium to remove the need of lead being added to the catalyst, while still keeping a very good activity. In this specific example, the metal content could be lowered by 90% in the reaction. And we are working on bimetallic catalyst, palladium platinum catalyst, where some initial indications show that you can, for example, replace 50% of palladium by platinum while keeping a similar activity and selectivity. And as you might recall, palladium is currently significantly more expensive than platinum. So if you can replace 50% of the palladium by platinum, and by doing that, still having the same type of productivity, you can again reduce your cost. So with that, I invite anybody who wants to ask any questions. You can also, if at a later time, you can send me an email to the email address indicated below. And if you do need R&D samples, we are more than willing to work directly with you. You can also go to Strem, www.strem.com/BASF, where you can find samples of those Nanoselect catalysts and other catalysts as well. And with that, I would like to thank you. And if you have any questions, let me know.
Thank you, Dr. Foote. It was a really good session. If there's any questions from the audience, we invite you now to use the Q&A function at the top right-hand corner of your screen. If you could put your questions in there, we'll be able to read them out. And we'll give about a minute and a half for those to come through. If there are none, then I'll wrap it up. But let's see if any questions come through. So the question box is in the top right-hand corner of your screen for the audience. Okay, it looks like we do not have any questions pending at the moment. So that marks the end of the session. Thank you very much to our presenter, Dr. Foote. Appreciate it. Thank you.